because I don't want to start talking and then, you know, it's no one's listening. So let me check. Just want to know if the live streaming is working fine and you're hearing me and so on. Okay, perfect. So yes, then I will start the talk. I'm very happy to be here, not really with you, but to be invited for this hackathon. And yeah, I'm going to talk about something a little bit more extended than what I intended, because I saw that actually have a little bit more time than what I anticipated. So I'm going to talk about many experiments we have done with analyzing and studying different states of consciousness. I will explain a little bit about that. And then I will talk about what I intended at first, that is the idea that, okay, obviously when you fall asleep, for example, you can find, using fMRI, huge differences in the functional architecture of the brain, which are interesting per se, because sleep is a state of unconsciousness and so on. But I'm also going to talk about how to prevent them, because sleep can be a confound in resting state experiments. So I'm going to also touch on that issue. So what I'm going to talk about essentially then is the functional architecture of the brain. I mean, spatiotemporal organization of brain activity in states of unconsciousness. Basically states of reduced unconsciousness, which will be, for example, deep sleep or anesthesia. But I will very briefly touch on what I consider states of enhanced consciousness that could be, for example, the psychedelic state. And finally, as I promised, I'm going to discuss the implication of all these results for classical resting state experiments. For example, if you have patients and you want to compare a group of patients against a group of healthy controls, how can you deal with the possibility that sleep is affecting your results? So, well, this is basically the people I've done this work with. This is the team I worked with in Frankfurt when I did my PhD, also a little bit after I finished my PhD. And well, this is me, the one I'm presenting the talk, but the work I've done is basically the combined effort of all these people. So the data I'm going to discuss is basically at first data acquired during sleep. So maybe you know what the human sleep cycle is about, but for those who don't, I'm going to briefly explain it. Basically, you are awake and then you start going through stages of deepening sleep. Deepening sleep means you are essentially becoming less aroused. You are losing consciousness, as you go into deeper sleep stages. It's harder to wake you up. And then you reach the deepest stage of sleep after about 1 hour, and then you go back, and then you enter what is called REM sleep, which is this little row here. This is the black part, and this is the part of sleep when you have dreams, mostly those dreams that you remember that are very like movie-like. And the the standard way to detect in which sleep stage a person is to use EEG. So EEG measures the field potentials at the scalp, while the currents associated with displacement of ions due to synaptic activity at the level of the scalp. And usually for a person that is awake, you measure a rhythm that is in the alpha range. And as you go deeper into sleep, essentially activity starts to become slower. In NG sleep, you start to have these very large amplitude events that I'm not going to talk about, but are very interesting. And finally, In deep sleep, N3 sleep, what I'm calling it here, you have this very slow oscillation, less than 4 Hz, and you can see it's a very simple and regular oscillation. Basically, it's going up and down. So, of course, if one wants to study the large-scale architecture of the brain, functional architecture of the brain, which is the standard method to study whole brain activity in humans, is fMRI, one has to handle the problem of doing EEG inside the fMRI scanner, and there is a whole optimized setup for this that we applied. I'm not going to touch a lot on this, but basically what one is doing is combining the two techniques simultaneously, EEG and fMRI and polysomnography. And we essentially put the people inside the scanner with the cap and all these other things around, and we managed to get EEG recordings that allow sleep staging inside the MRI scanner. So we have fMRI during sleep. So we have lots of subjects. This is a detail of 39 subjects. And you can see that they have certain time in minutes in wakefulness, but they also go through deeper sleep stages. And some of them, here, some of them are even 20 minutes or more, up to half an hour in even deep sleep. So this is a very interesting data to look at also deep sleep. So the methods we use for analysis are very classical in the field. For example, we can take a brain parcellation, and then we have the hypnogram. The hypnogram is basically as a function of time in which sleep stage the person is in. In this case, the person starts awake, then falls asleep, and finally reaches N3 sleep. And we just take a chunk of the data that corresponds to, for example, deep sleep, N3 sleep in this case, and we compute the correlation between audible signals between all regions of interest, and we have a correlation matrix. This is a standard type of analysis. And we have done this, for example, as a very exploratory analysis within different resting state networks. So you probably heard a lot about resting state networks, and I assume that you're familiar with that. So I'm going to just skip it. But within different resting state networks, we take the regions of interest that belong to visual networks, sensory motor networks, the fault mode network, and so on, and we study the connectivity within the networks. So in this example, I'm looking at the connectivity at N1 sleep. So what is above the diagonal here is simply the correlation, the functional connectivity between the pairs of regions in N1 sleep, and what is below the diagonal is a statistical comparison of N1 versus wakefulness. So blue means that connectivity decreased during sleep, and red means that the connectivity increased during sleep. So we see that actually for early sleep, we see lots of connectivity increases in different parts of the brain, but we have also very salient features, that is, for example, loss of the connectivity of the thalamus, which are these two rows, with large chunks of the cortex, basically of the fault mode and auditory regions of the brain. So this is well known, this has been investigated. This is basically what allows the transition from wakefulness to early sleep. It's related to loss of arousal and disengagement from the environment. Then we have another set of results for N2 sleep. I'm not going to touch this in detail. And then for N3 sleep, we have another set of results. You can see that in deep sleep, basically connectivity between most parts of the brain within the regions of interest at least is lost. So this is very exploratory, and it's hard to, well, it's not hard to make sense of this, but it's not really hypothesis driven. So we didn't attack the problem at first based on some hypothesis of what we would observe during deep sleep. So then we asked the question, okay, for example, what happens? So this was all within network changes, so changes in the connectivity within these different networks. So we asked what would happen if we looked at between network changes. For this, basically, we performed the same set of analysis, but then we applied binarization to get networks, so binary networks. This is simply by putting a 0 in the matrix if the correlation is below a certain value, and a 1 if it's above a certain value, and this value is decided by the density of links we want in the network. So with this network can be very dense, meaning that the threshold is very low, or it can be very sparse, and this is the density of the number of links divided by the maximum possible number of links in the network is the parameter we use to select the threshold. And I'm saying this will be used to study between network connectivity or interactions, because what we did was an analysis of the modules of the network. So once you have a network, so these small circles here represent parts of the brain, for instance, you can try to find the subsets of regions that are more well connected among them, but weakly connected with the rest of other similar tightly connected regions. And this is what is usually in the physics literature is called a community decomposition or a modular decomposition of the network. You see that what you find makes sense. You have this becomes one module, this becomes another module, and this becomes another module. If we were to look at the modules, they will look actually relatively similar to the resting state networks. And we not only have the modules, but we have a number here that tells us how well we could split this network into modules. So the higher the number, the more separate these modules are. We see that if we change some of the connections from within the modules to between the modules, so we rewire some of the connections, for example, this connection here, we put here, connecting the modules and so on, we see that we still find the same modules, but of course the modularity value is lower because the modules are less separated. And what we find is that during early sleep, this modularity as a function of the link density we use to construct the networks stays the same. It's not different from wakefulness, but N2 sleep and N3 sleep, which are these two panels, have a higher modularity, so the networks become less integrated. And this is interesting because there could be a link with, well, we studied this because a possible link with information integration theories of consciousness, such as the theory of Tononi. I'm not going to go into detail, but the theories basically says that consciousness is related to the capacity of the brain to integrate information. And if the networks become extremely modular, of course, there is a loss of functional integration. And it's also interesting that during N1 sleep, during which you still have some residual consciousness, you don't see the changes. But in stages that are characterized by not by a complete loss of consciousness, but by a dramatically diminished level of conscious awareness, you see that the modularity is increased. So then we asked, okay, this is all spatial, related to changes in the spatial organization of the brain. What about the temporal dimension during sleep as measured by fMRI? So the temporal dimension actually is what is most informative about the EEG. So these slow waves, for instance, you will see all around the scalp. So this is mostly a global phenomenon that you see using EEG. And the informative part is actually when you look at the temporal dynamics of this thing, you basically see a loss of complexity. You see things going up and down, like a bistable thing. So what about fMRI? Basically, well, as I said, there are very different EEG dynamics across sleep. So what about fMRI? So to study the complexity of the fMRI signals during sleep, we applied some methods well known to physicists, which aim to find how strong the temporal correlations in a signal are. So basically you can have a signal with very short range correlations. For example, if the signal at a given point in time depends only on what happened before, or you can have a signal that has, what happens at a certain moment in time depends on what happened minutes or even hours before that. And this is kind of dynamics are basically dynamics with long range correlation. So we applied a method that is called the trending fluctuation analysis, which has some advantages. I'm not going to go into detail on the method, but basically you end up having a number which is called h from Hart's exponent, and if this number h is larger than 0.5 and some other assumptions hold, then you can say that the signal has long-range memory, meaning that, again, that the signal is not influenced by what happened in just the previous amount of previous moment in time, but over a longer time in the past. And this is very typical. So signals like this with long-range correlations are typical from the brain. EEG signals, MEG signals, intracranial recording signals, and so on, even signals related to human behavior, like the errors you make in a certain task, all have these kind of long-range correlations. It is known that fMRI signals do present these kind of temporal correlations as well, and we wanted to see if during deep sleep these correlations remained or not. I'm going to tell you in a while why we think this is important. So this is actually what happens for the whole brain. This is a histogram of the values of the Hertz exponent across the whole gray matter of the brain. The black plot is the histogram you get in wakefulness. You see that most voxels have a Hertz exponent that is larger than 0.5, meaning that there are signals with long-range positive autocorrelation in those voxels. And as you start falling asleep, you see that the distributions, the early sleep is green, then you have blue N2 sleep, and then you have red N3 sleep. These distributions start to become shifted towards having a peak at 0.5 Hertz, which is signals with basically lack temporal correlations. And we also put a phantom in the scanner, which is just, you know, a bag with water. And these have, of course, a peak at 0.5 because the voxels, the signal that you measure in a voxel with water doesn't have any sort of meaningful temporal correlations on average. And the peak of these histograms, you know, show a nice decreasing trend. When you go deeper into sleep, you start approaching loss of temporal correlations in the brain. And this is of course interesting because basically for two reasons. But the reason I think is most interesting is because there are, from an intuitive standpoint, the integration of information in time does seem to be a necessary requirement for consciousness, but also a sort of temporal continuity. Also, you know, it's not like consciousness is associated with the fleeting change from one scene to the other, but there seems to be some sort of smooth thing going on. Imagine how it would feel like if what you experience consciously depends only on what you experienced 1 second before. So this sort of temporal flow, we think it might be captured by these techniques, and it's lost during deep sleep. And where is it lost? Sorry. Well, this is actually rational specific. So if we look at where we see this decrease in Haas exponent in N2 sleep versus wakefulness and in N3 versus wakefulness, we see this bilateral parietal cortex and also this blob in the precuneus and in the inferior part of the frontal gyrus and the thalamus and so on. And these regions have a certain overlap with what is called the default mode network. So this is one of the resting state networks, and it's very important in the field of consciousness because it is known that for a wide range of states of reduced consciousness, call it sleep, the vegetative state, general anesthesia, and also certain types of epilepsy, metabolism, meaning glucose consumption, is decreased in this network, in the default mode network. And this network is also very famous because tasks basically deactivate this network as opposed to other resting state networks in the brain. So this has a strong overlap with the frontal parietal cortex. So it has a frontal part and a parietal part and a part in the posterior cingulate cortex. And this network is also very important because it forms the basis of what's called the global workspace in other theories of consciousness, meaning that once a stimuli enters the brain, starts to percolate, and when it reaches this network, it basically enters conscious awareness. And the perception leads a temporal sustained reverberating activity in the default mode network. So loss of temporal correlations could also mean that in the global workspace, basically you cannot have any more stimuli that is entering and leaving a temporally correlated trace. So of course, well, this is just a simple summary of what I've said so far. But something that I believe is very interesting is how does functional connectivity relate to structural connectivity in sleep? Mostly because of that, of the following. These resting state networks that I'm showing here in the first row, they actually, I told you that changes in connectivity within them can be observed, and also connectivity within and between the resistive networks. But if you apply, for example, independent component analysis to sleep data, you will still be able to find the networks. So there seems to be something that's still letting you find the networks even in states of deep unconsciousness, not only sleep, but also anesthesia or even comatose subjects. So what is going on? Where our hypothesis is that these resistive networks are actually somehow encoded already in the structural connectivity of the brain, meaning, you know, the white matter of the brain. At some point, we built a simple model, and this model, under very general assumptions, which are the assumptions of criticality, basically, allowed you to recover these networks with a very basic computational model. So it seems to be that somehow, if the dynamics are real enough, but still very artificial, you can still manage to find these resistive networks based only on what we call here the hardware. So to say that the hardware, which is the structural connectivity, is predefining the software, which is the dynamics and the resistive networks. So we try to investigate this issue by comparing how structural connectivity, that comes from DTI, relates to functional connectivity coming from fMRI in deep sleep, or in states throughout the different stages of sleep. So basically, what we are asking is, we have on the left side of the equation, we have a whole brain binary connectivity matrix. This is a matrix derived from some like 40 subjects using DTI. Is the average of those subjects, and this is binarized, and well, there is an intensity representing the number of fiber tracks showing in each pair of regions. And then we have, on the other hand, the functional connectivity matrix that is based on fMRI data, and this is acquired during wakefulness and also during sleep, and we want to see how these two things relate to each other during different stages of sleep. And basically, I'm showing here on the inferior lower part the DTI matrix, and on the upper part the functional matrices during wakefulness. And then I'm showing, again, above the diagonal, different stages of sleep, and below the diagonal I'm showing the statistical comparison. So basically, in which regions we find the difference in N1 sleep, N2 sleep, and N3 sleep. And we label them differently depending on whether this change in connectivity is located between two regions that are shared direct anatomical connection or not. So this can be summarized as follows. If it's true that these resistive networks remain because of the underlying structural connectivity of the brain, then what would be happening is that we could lose some of the connections, which are in red, the functional connections. We could lose some of the functional connections that are connecting pairs of nodes that are not related strictly, nor connected strictly through direct anatomical connections, but we might not be able to lose the functional connections that are connected directly by anatomical connections. So basically we start pruning the network, and cutting the functional connections, but there is a limit, and this limit on what we can cut is imposed by anatomical connectivity of the brain. If this is the case, this would explain why we actually see the resistive networks still during deep sleep. And this is actually the case. So for example, the regions, the probability of finding a region that shows a connectivity decrease during sleep is actually higher when you don't have an anatomical connection, for example, in deep sleep, than when you have. So basically you lose preferentially connections that functional connections that do not have anatomical connections, and actually it's the opposite for those connections that are directly connected with structural tracts. So it's not even that you lose the functional connectivity between the pairs of regions that do not share a direct anatomical connection, but you also strengthen the ones that have a direct anatomical connection. And we ask, okay, if this is a regional effect or this is a global effect. And what we found is that we managed to find this, to study this at the local level, and we found that in a set of regions that is very similar to the full network, what happens is that you lose the similarity. So things do not become more similar to the anatomical structure, but they become less similar to the anatomical structure. And the opposite happens in a set of regions that is very similar to the, well, it contains all the primary sensory cortices. So there seems to be dissociation. Some parts of the brain during deep sleep become closer to the underlying anatomical structure, and some regions become less similar to the underlying anatomical structure. And if we want to ask why, well, it's difficult to ask why, but we think it has to do with the fact that during sleep, some parts of the brain basically lose this sort of critical dynamics, and some parts of the brain actually are more efficient. Especially the sensory cortices are closer to critical dynamics during sleep. So this means that the functional and structural networks will look more similar, and this is because it makes sense that these dynamics are more critical at the sensory cortices during sleep, because it makes it easier for a person to be awakened in case there is some environmental danger during sleep, and the fact that critical dynamics are lost in the default mode network during deep sleep might account for the fact that basically you become unconscious mostly during deep sleep. But this is a very, very hypothetical, and we built at some point a model to test this thing, but you know, it's still very preliminary. We found the same result, a very similar result with mostly frontal areas using propofol anesthesia, and we recently I've been working on replicating these results in patients with disorders of consciousness, and again there is a loss of temporal correlations in disorders of consciousness, for example, and when we look at the structural and functional similarity, we find very similar results in propofol sedation and in patients. So if this holds for states of enhanced consciousness, well, we would need to define what is a state of enhanced consciousness. And we have been working with people in London trying to prove that many of the things that you can see during deep sleep or during anesthesia, essentially during loss of consciousness, you know, this loss of complexity, this loss of temporal rich dynamics, this increased segregation between modules, they go in the opposite direction for states such as the psychedelic state, which for some reason we have hypothesized to be more entropic in a way than wakefulness. So we found actually some of these results. I'm not going to go into deep detail, but we found the opposite results using psilocybin and using LSD as well. So then I'm going to finally talk about the last part of what I put in the title. So I've already told you that this functional architecture of the brain is deeply changed during states of unconsciousness, but the question is, how can we avoid it? Because if you have, I don't know, you're interested in studying, for example, patients with I don't know, to make it easy, patients with insomnia and patients who are healthy controls, good sleepers, and you put them in the scanner, it is more likely that the good sleepers fall asleep more often than the patients with insomnia. So when you compare the resting state data from both groups, you might be actually reporting only differences related to sleep, not to the disorder itself. So the question we ask is, okay, how can we find out if a person is falling asleep inside the scanner without needing to do this solving the technical issues of combined EEG and fMRI. So what we did is we took connectivity between parts of the brain. We tried to support better supervised machine learning algorithm with data that was labeled as different stages of sleep. And we basically trained the computer to build hypnograms based only on fMRI data. So this has a nice high performance. So this is, for example, a plot that shows as a function of time the number of subjects in our data set that managed to maintain steady levels of wakefulness. So basically this is a decreasing function. This function decreases when one of the subjects in the sample fell asleep at least once. So, you know, at some point during 10 minutes, after 10 minutes, we know that 40% of the subjects fell asleep at least once. And this is worrisome at first, the blue plot, because it means that actually sleep happens a lot. Our subjects did not receive the instruction to fall asleep. They just received the standard instruction to close their eyes and relax. And they fell asleep. I mean, after 10 minutes, half of them more or less fell asleep. And the machine learning classifier predicted, when trained and used to build hypnograms, had produced a very similar function with an 87% match. So what we did is we focused on what is the length of a typical resting state experiment, around between 5 and 10 minutes. And we downloaded data from all around the world using the kindly uploaded data from different groups that is comprised in the 1000 functional connectome project. There is around 1,100 subjects in this dataset coming from all the cities here. And we applied our classifier to detect sleep to this large database to see if this is really a huge global problem or if this is just us basically having the problem of sleep confounds. Well, you might not see here, but there are little pie charts showing the amount of sleep observed in each of the centers, but I'm not going to discuss this in detail. But for example, if we plot this function, the probability of being steadily awake in our data, it has, of course, after 5 minutes is 60%, and we have a similar decreasing trend in the connectome data. So we start to verify that for the connectome data and the Frankfurt data, which is the data we acquired in Frankfurt using EEG fMRI, there is a tendency in both of them of subjects falling asleep. This is the probability of observing, for example, a subject losing wakefulness in our data, and this is the probability of observing a subject falling asleep in the connectome data. And there's a slight decreasing trend. Well, the decreasing trend is more obvious in the Frankfurt data, but there is a slight decreasing trend in the connectome dataset. There is a clear increasing trend of finding N1 sleep in both the connectome data and in our EEG fMRI data. And deeper sleep stages are essentially either flat or, well, basically noise. So I don't think this means that there is N3 sleep in the connectome data. It simply means that, of course, the classifier makes some mistakes. But basically, this shows that we have trends that look like there is actually sleep in resting state experiments that are supposed to be performed during wakefulness. So we did we categorized basically all the centers in the sample, and we observed, well, this data is available. We have the probability of people falling asleep for each of these centers as a function of time. And we observed that, for example, those MRI centers who asked subjects to keep their eyes open still had sometimes a decent amount of sleep, but having eyes opened and fixating on a cross, basically all the centers that use this paradigm of fixating on a cross had almost zero amount of sleep. So this seems to be maybe a good strategy to avoid to avoid sleep confounds, asking subjects to fixate on a cross. So, well, the implications of this are quite clear. If you do an fMRI experiment and you ask your subjects or patients to close their eyes, you should expect that after 5 or 10 minutes, half of them will fall asleep, unless you manage to prove otherwise. And based on all that I discussed before, all these functional architecture changes during deep sleep, of course, this is a huge problem if you are comparing a population that has a different level of sleep propensity than the other population, as in the example I gave before of insomnia and healthy, good sleepers. So there seems to be a problem here. So how to solve it? Well, one way to solve it is to, for example, use simultaneous EEG fMRI like we did. If you use simultaneous EEG fMRI, then you can separate those moments in time in which your patients or subjects were awake and when they were in deep sleep. But this seems to be difficult because you need equipment and you need the expertise to set up the simultaneous EEG fMRI. So the question is, can we do without EEG? And of course we can. And there is already an obvious way to do it, which is applying our supervised classifier to the data. The problem with this is that our supervised classifier was trained with data using our Siemens 3 Tesla Trio scanner in Frankfurt. I mean, if you have a different scanner or you have a different sequence, it's not guaranteed that our machine learning classifier will generalize well to your data. So what we recently developed, and this was what I was going to talk about mostly in my original talk, is an unsupervised method to find whether your subjects are falling asleep or not. And it's actually very simple. Suppose you have a sample of patients or subjects, I don't know, let's say for example 50, which is not an extremely large amount. Then what you do is you use a sliding window. So you have a window, a part of this wall time series, and within that window you compute the connectivity between all pairs of regions in a template, and you start moving this window, and you have different connectivity at different amounts in time. And then you apply a clustering algorithm to this. And we use, of course, 4 clusters, because we want to show that these clusters, well, at the end of the day, these clusters correspond to wakefulness and the 3 stages of human sleep. So the aim is then, of course, to match these clusters to the sleep stages that we have labeled using EEG simultaneously. But I show you a way in which, if you do this and you find certain patterns, you will not need the EEG for validation. So you can do this in your data without any simultaneous EEG fMRI. So when we do this clustering, basically we have then these four states that we can detect by clustering the dynamic functional connectivity. And then we can look, for example, at the probability of observing wakefulness over the whole sample and the probability of observing one of the clusters, which is the cluster that, of course, corresponds to wakefulness. And we see that they follow very similar temporal trends. So, of course, wakefulness as a function of time in our sample is decreasing because subjects tend to fall asleep, but the likelihood of observing this fMRI cluster is also decreasing, and it more or less is matching what happens using the EEG. And this happens for all sleep stages, for N1, for N2, and even for N3. And the average connectivity that we find by looking at the connectivity in sleep labeled by the ground truth, which is the EEG, we have connectivity matrices which are extremely similar to the clusters we find using the dynamic connectivity approach. So basically this shows that if you have data, if you have 50 subjects, for example, you should, and you suspect that some of them are sleeping, you should do this dynamic connectivity analysis, perform a clustering, and see the likelihood of the different clusters appearing over time. And in case you see a cluster that has a clear decreasing trend in time, a cluster that is less likely to be observed in time as the experiment advances, then you should suspect that this cluster is detecting sleep. So once you find clusters that might be representing sleep, you can simply look at the subjects who have had the highest prevalence of these clusters and exclude them from the analysis, or you can just cut the moments in time in which these clusters are present, and you can, using this unsupervised algorithm, basically try to remove clusters that represent sleep in your data. Okay, so just to summarize, we found that, of course, unconsciousness leads to widespread changes in the functional architecture of the brain, that these changes make sense in terms of certain different theories of consciousness, that these changes are consistent between different states of unconsciousness, such as sleep, anesthesia, and we are now working on disorders of consciousness. And there are implications for classical resting state fMRI studies. That is, you don't want these changes to happen if this is not what you are studying. If you are studying something else, you don't want your subjects to fall asleep. But we have shown that this is a problem, that a large database apparently has a substantial amount of sleep. But we have also shown a couple solutions that will let you, without combined EEG, simultaneous EEG, try to find and eliminate the sleep from your resting state fMRI data. So that is all, and thank you very much for listening. So I'm now going to to the Hangouts to see if I don't know, if you have questions or something. Maybe Asier can get in touch and transmit them to me. Okay, so there is a 20-second delay, which yeah, you have to be patient. So did everything went well? Hi, you're still there? I suppose he's typing. Yeah, no problem. Yes, well, if I understand correctly, the question, yes, resistive networks are preserved during deep sleep. By preserved, I mean that you can still find them using, for example, ICA. This doesn't mean that the intensity of the networks is the same. There will be changes, but the networks are still there. And the same happens in anesthesia. So what it seems to be happening in both situations, yes, is in fact a reduction of the connectivity towards the baseline, so the backbone of the anatomical connectivity. We showed this in our paper, and a very beautiful paper in monkeys published by the group of Stanislas Tehen in Paris showed the same result for propofol anesthesia, basically that during deep sleep and during propofol anesthesia, the functional networks resemble more the anatomical backbone. If there is something to learn about the similarity between anesthesia and deep sleep, well, it seems to be that both conditions reduce the functional connectivity of the brain, but they both hit a limit, and the limit they are hitting is basically the structural connectivity of the brain. And it's important that they hit this limit and they do not go beyond that limit, maybe because this might be like something you don't want to lose if you want to still be able to recover consciousness. Maybe in patients with a source of consciousness that have lesions in anatomical tracts, maybe you can get an even deeper dissociation between structural and functional connectivity. But for deep sleep, globally, I mean at the global network level, both deep sleep and propofol anesthesia seem to be doing the same, seem to be reducing connectivity, but not being able to go beyond the anatomical backbone of the brain. That is the answer, basically. Consequences may have in long resistive series from last years where this disconnectivity had not been accounted. Okay, so it's difficult to do finger pointing to studies saying your study is not valid because it looks like your patients fell asleep. This is very difficult to do because we don't have any proof. I mean, we do not have any proof whatsoever that, for example, I don't know, we were able to find, for example, a very well-known study in patients with autism showing that the changes in the thalamus happened in patients with autism, and also changes in the connectivity of the thalamus are very common during, in people falling asleep. So if we wanted, we don't want to, but we could, tell or say, okay, this could not be autism, this could be because, the autist patients are less prone to fall asleep than the healthy controls who are more relaxed, and this is very difficult to do. But there are certain areas of research in which I believe this has to be done. One area of research is fMRI resting state studies of sleep deprivation. You cannot do a study of sleep deprivation and then follow the standard resting state paradigm of asking subjects, closing their eyes and being inside the scanner and not falling asleep, because the sleep deprived subjects will most likely fall asleep. And it is well known and documented that people are not very good at judging their own level of sleep. So once you realize that you have lost sleep, you might be in quite a deep sleep stage, and you might not even realize that you fluctuated from wakefulness to early sleep. And if you look at the literature of sleep deprivation studies, this is an area of research in which you have lots of articles following this paradigm of asking subjects to close their eyes and not fall asleep. And many of the results in the literature are actually very similar, very consistent with sleep-deprived subjects falling asleep. Even more, we recently collaborated with a group doing sleep deprivation studies, and we asked them for the data of the sleep-deprived subjects and the subjects without sleep deprivation, and we applied our machine learning classifier, and indeed we found higher prevalence of sleep in the sleep-deprived condition, which is not surprising. So this is an area of research that, in my opinion, it's probably extremely contaminated by sleep conforms. So that would be my answer to the question. Hi Jesus, how are you doing? We don't know, that's the answer, why these changes in structural functional connectivity are selective. We don't know. There seems to be a specific function of the regions that have different trends, that you have the sensory cortical areas with increasing similarity and higher order areas of the brain with decreasing similarity. And we can hypothesize, as I said before, that this loss of similarity in higher order areas of the brain represents or is related to loss of consciousness, and that a more tight connectivity between a more tight relationship between structure and function in sensory areas is related to increased susceptibility to sensory stimuli, meaning that you could wake up more easily if you are sleeping. But other than these hypotheses, we don't know, and we are keen to do some modeling studies to try to relate this structure and function connectivity to different parameters of more realistic models, such as that include, for example, inhibition and excitation, and try to find if changes in inhibition and excitation, if these regions can account for this dissociation between structure and function, and try to see if these changes in excitation and inhibition actually happen physiologically during sleep. But this is work in progress, so we don't have yet a definitive answer to your question. I'm not sure I get the question. So the question is if the machine learning classifiers would be able to work with other metrics, such as the temporal metrics and so on. Did I get if we could base the classifiers on these other results I mentioned? Is that the question? Because I'm not really sure I got it right. So I don't want to answer something that is not what was asked. Maybe if you can clarify a little bit the question. Okay, good, thanks. Yes, the problem with these metrics is the following. You don't want to use dynamics for the machine learning classifier because you want a good resolution for the sleep station using fMRI. So you want to have short windows of a small number of volumes that you can slide through time, and within each window find the prediction of your sleep classifier, of what is a sleep stage. And connectivity between a few volumes, like 50-60 volumes, well, you can find. I mean, it's not optimal, but you can measure correlation between 50 points. But these Harsh exponent metrics, by definition, if you want to look at long-range temporal correlations, you want a long temporal sample, so not 50 volumes, but as many volumes as you can have. So this might work very well in principle, but it will not work in practice because the windows you want to use are too short. So it doesn't make any sense really to try to do it using at least the Harsh exponent, because it's again, the resolution will not be high enough, basically. Okay, thank you very much, guys, for listening, and I hope you can enjoy the rest of the meeting, and I hope to see you soon. So I'm going to stop the streaming now, and thanks a lot for being there. Bye bye.